Good afternoon, ladies and gentlemen. I am Ramesh Malla, a professor of structural engineering, applied mechanics in the Department of Civil and Environmental Engineering at the University of Connecticut. I would like to recognize my two co-authors, also the Oliveira, Ph.D. student, and Santosh Dakal, master students, working under on this project under my supervision. Today's presentation title will be Dynamic Characteristics and Response of More Than Century-Old Truss Railroad Bridge Structures Under Service Loads. I will follow the regular presentation style. I will start with background importance of the research, give you project objectives, present some little bit theory on dynamic analysis and data processing, look into the bridge we have selected for field testing, present you some field test sensor devices, some results from field testing, move on to finite element modeling with the bridge, discuss about the results, compare them with field testing. Finally, I will present summary, conclusion, and acknowledgement. About the background and importance, as you all know, railroad transportation being critical and vital for the U.S. economy for a long time, and it continues to be significantly important for future. The Northeast Corridor rail line from Washington to Boston is the busiest passenger railroad corridor in the United States, and US DOT federal FRA has designated NEC to be the highest priority for upgrading to high-speed train line. There are a lot of old bridges, more than 100 years old bridges in this Northeast Corridor, especially in New England, and it's very vital to upgrade these and monitor these bridges to maintain them to their full capacity for the viable, thriving economy for the region as well as for the nation. Also, the importance of the research is for load rating of the railroad bridges. This research presentation I'm doing today is under TIDC Project 1.2, Condition Health Monitoring of Railroad Bridges for Structural Safety, Integrity, and Durability. The main purpose objective of this research is to develop an efficient and cost-effective methodology for short-term and long-term structural response, condition monitoring, assessment of the railroad bridges using various methodology. And for this purpose, we have taken a methodology of selecting bridges, doing some material characteristics, finite element modeling, field testing, and then finally the structural response, and try to get the information on the durability of the structure. And today's specific presentation objective is to present you some results from our field testing and the process of developing finite element model. Just to give you some brief theory on dynamic analysis, we'll begin with the regular dynamic equation for multi-body freedom system, the mass matrix, acceleration vector, damping matrix, velocity vector, stiffness matrix, displacement vector, and forcing function on the right hand side. And for frequency in mode shape, we look into the undamped free vibration. That means Ft becomes 0, C becomes 0. The equation is as shown here. And with proper substitution for displacement U, we can obtain that equation in the form shown in step 3 here. As you see here, omega is the frequency and Phi is mode shapes. So solving this equation, we can get the frequency and mode shapes. If the structure has a pre-stress, for example, the bridges for permanent load gives some pre-stress, and at some additional mass, such as the train mass on the bridge, then the equation 3 could be transferred to equation 4c. As you see here, the S is the additional stiffness due to the pre-stressing, and the capital M is the added mass, in our case the train mass. Going to next slide. For the data processing, usually in the field, as you know, we measure data in terms of time. For example, the displacement maybe in terms of time here. We measure velocity, we measure acceleration, but the more efficient will be transforming this time domain quantity into frequency domain, which is shown in equation 8 down here. The Fi omega is your frequency domain quantity. The good thing is if you plot the amplitude with the frequency, then you have a distinct peak at the particular values of frequencies. So it's easy to pick up the frequency from this kind of transformation. Another way is if you know the input and output. Output, usually we measure, right? Displacement, velocity, acceleration. And if you know input, forcing function coming, for example, we can obtain this transfer function, and transfer function is related to frequency. So looking into the bridge we have tested, we took a bridge, Devon Bridge in Connecticut over the Housatonic River. The bridge is between Milford and Stratford. The bridge is 7-span, 1,067 feet long. There are two identical bridges side by side. If you look at the diagram here, we chose for our field testing span 7, which is east, next to the east abutment, and this bridge was built 1907 and is owned by Connecticut Department of Transportation. We did a series of tests on this bridge, as you see down in the table here. October 28, 2020, January 23, 2021, January 8, 2021. The first test we did was using 3D laser scan, the laser vibrometer, scanning vibrometer. And second test we did was using the standalone acceleration. And third test in June 8th we did was using single point laser vibrometer. So giving you more figure or the more introduction of the bridge. If you look at here, as I mentioned, two bridges side by side on the top left, and in the top right you will see a typical span of the bridge. Is truss kind of bridge span. It's very interesting construction this bridge has. If you look at the bottom chord member, it's not a single member. If you look at the left side here, bottom row, you will have series of I bars. So the I bars goes from 6 I bars towards the end to the maximum of 10, I think 10 I bars in middle of mid span. And also if you look at the floor beam going from one truss to another truss, the floor beams are not uniform cross section. They are tapered in a sense. Some of them are tapered and some are uniform cross section. And you will see here the floor system of the bridge, rails, ties, and so on. And just give you some idea of the different trains go over this bridge. The Amtrak Acela travels here, and Acela has engine left end and as well as the right end. So the engines are very heavy. And then Amtrak Regional, which has engine one end. And Metro North, another passenger train. Metro North have all cars identical, and it doesn't have an engine because it runs using electricity. Now you're looking into the loadings coming through the axle of these trains, and the axle configuration. I have shown here 3 diagrams. Top one is for Amtrak Acela, the middle one is for Amtrak Regional, and the last one for the Metro North M8 train. So the values of axle loads given and axle spacing all given here. So these informations we use for our for the concept wise. I'm not go to that because of time limit here. So let's go to the field testing results here. Test 1 setup October 28, 2020. We use 3D scanning laser vibrometer. As you see here, one of the vibrometer here and the bridge span over here. We shoot the beam and the beam reflects back, and the device will measure the frequency shift. Down here, one of the vibrometer we put in the man lift on a raised platform, two of them on the ground. So that measures velocity response. From there we get frequency. So looking at some results here, this is when the bridge was under trans excitation. So you have a distinct peak, as you see here, different values of frequency. So you can easily identify the frequencies. Now the right side plot is under the shaker. We put shaker on the bridge, vibrate the bridge, and we can get a particular frequency. Now left side, you see the data here, frequency data measured from the train excitation and measured from the shaker on the bridge. Shaker on the bridge for reference, so to calibrate basically. So these data are pretty close. I would say first 1.8 from the force vibration from the trains, and from the shaker we got about 1.5, and second 3.125, and from shaker 3.25, and so on. Now you will see here the response from the laser vibrometer of the bridge vibrating. Of course, this is the exaggerated motion. Doesn't vibrate that fast, that big. Next slide, we did testing January 23rd, 2021. Luckily, the weather was good that time, even this winter. Using the 5 standalone accelerometers, as you see here, the green dots. We put 4 of these on the front side. One was on the back side of the other side, the truss, the other side of the bridge. Then we measure the accelerometers. We still need to analyze this data. We did some analysis, but we still have to do it. So we didn't have the other results. So as you see here, the accelerometer attached. The third set of tests we did was on June 8, 2021. In this day we did testing using single point laser vibrometer. We measure axial displacement of the bridge, as you see in the right figure. This is the laser system underneath the bridge. We try to measure the displacement at the bridge here. So we focus the laser beam at different points, as you see here, point 1, 2, 3, 4, 5, half of the half span of the bridge. The other we couldn't do that because there was water underneath those points. So we measure velocities. From velocity we measure displacement. This slide shows some of the data we collected from this test on June 8th. It's a velocity measurement, velocity plot with time, and we did a high-pass filter to get it to noise. Then we integrated that to get the displacement. We measure the displacement, and we're showing some sample results here. Under 3 trains, train 1, 7, and 10, they were the laser was focused at the vibration point 1, which is next to the apartment, and a little bit inside vibration point 3, vibration point 4, and the table up on the right shows the values of displacement we receive. Now if you look at the displacement plot, you will see the up and down. There are 8 cars, by the way, these trains, and the results we got looks pretty consistent, so gives some confidence measuring displacement using. So now let's go and talk about how we develop finite element modeling. We use the software package ANSYS. We did static analysis, pre-stress modal analysis, also the added mass modal analysis, and transient dynamic analysis. We had some design drawing done in 1905. It's quite interesting looking drawing here. And the whole bridge system is built in a very interesting way. Draw all these composite sections and bring to a nice shape, equivalent shape, which we can input in ANSYS. Quite laborious work generating ANSYS finite element code. Then material characteristic, what we did was we got certain samples of bridge materials. We tested that in our machine, testing machine. We found out yield stress and ultimate stress and the modulus of elasticity from these curves, and we compared those available in ANSYS, and they came pretty close. If you look at a percentage difference, not that much. So we choose this value here shown in the bold faces. For the modeling, geometry modeling part, we consider the bridge simply supported. One side they have pin connection, on the side is roller. So roller rolls in the x direction, displacement is released, and we consider loading on the trains coming through the axle. As I mentioned, we did static, dynamics, pre-stress, and added mass analysis. I'm not going to repeat that one, but here again, added mass analysis, we try to cover the whole bridge with the train. The 12 axle come into play, and then we apply the added mass from the train, added mass from the ties and rails. Actually, in our model, bridge model, we don't have ties and rails still, so we had to add the mass coming from there for our modal frequency analysis. So in static analysis, the self-weight of the bridge is computed by ANSYS. 200 pound per linear foot. Each track was put in addition to account for track, rail, and fasteners. And 243.42 pound per linear foot used for the wooden ties specified by CONDOT. So the displacement, static displacement came to be 0.594. Then the frequency mode shape analysis, there are a lot of values here. I didn't want you to be too much concerned about these. The main important thing, we're trying to compute the global or identify the global frequencies here. In three cases, as you see, a reference case and a pre-stress case means you apply this additional permanent weights or loads. Another is a added train mass case. We identify general global frequencies here, global lateral 1 in this case, global lateral 1 in the third case. As you see here, then global 2 we identify here. So all the three cases, even though a lot of values here, I try to identify the global. Now this is a really tedious job because we have to look into every single one of them to see whether they are local or global. This slide shows several of the mode shapes. Let's concentrate on the last two on the bottom to determine the local and global. The left side shows the global and the right side shows the local. Let me see whether we can play the video here. All right, as you see, whole bridge vibrating there. Here, some of the on the right side, some of the members, local members, are vibrating. So that's the way we determine local and or the global frequencies. For the dynamic analysis to compute the displacement, what we did here in the finite element is we try to get the loading functions, these triangular loading functions with varying time, where the load or the axle or the wheels are coming in touch with the bridge. We started with the different speed of the trains. So this particular thing we are showing here are for the 31 mile per hour train. the 2 cars, Metro North 2 cars here, Metro North 8 cars. So these pulses, as you see here, the ANSYS, with the one thing we got into the ANSYS software package. So these loads are applied at the various nodes along the length of the bridge. So that is a loading function. Based on that loading function, we determine the displacement at different nodes of the bridge. It's a tedious job, very time-consuming job to create this loading function. As you know, it's a moving load from one point to another point, and there's a lot of axle loads. We have to create that axle loads in triangular fashion, and the time duration of each pulse is depending on the speed of the train. So we got what we did then is we measured the the displacement at the mid-span of a floor beam. That means basically middle of the floor beam, and we got a response. As you see here, it's very close to what we got in the from the field testing. The amplitude is a little different here, smaller, because in the field testing we measure right on the along the this line here, but this one is right in the middle of the floor beam. Please keep in mind the train has 2 tracks, okay, this side and that side. So when the train comes right over this track, so this side would deflect more. So discussion and comparison, again, as I mentioned, frequency in mode shapes, they came pretty close. Field line FEM, very close result we got. As you see here from the field test and the FEM model, the values are pretty good. The reference, pre-stress, and mass and the added mass of the train. So that's and the frequency mode shape very well. Now response for displacement, the pattern comes very well, right? The displacement pattern. The amplitude, we may have to check a little bit more. Maybe a little bit more study needs to be done and to verify whether amplitude come similar way. Now in summary, in conclusion, as you see, we studied this 115-year-old long span through Truss railroad bridge, and we did some material testing. We did field testing using laser Doppler vibrometers and 2 kind of accelerometers. We developed finite element models. Frequency mode shapes we obtained from both methods, and they are in good agreement. Displacement we measured using the laser vibrometers. We also developed the train loading, the moving train loading, depending on time and the speed, of course. So the pattern, the displacement pattern came pretty good. We still have to verify the amplitude we got from the finite element analysis. Future work, we need to refine our finite element model, including the float system, which are ties and rails. We need to develop the forcing function, the forces coming from the axle, considering the interaction between bridge and the train. As you know, the bridge vibrates, train vibrates, right? And they are a coupled system. We need to do that and then use the methodology we developed for another bridge. We are using the trying to use the bridge cost curve, which is shown on the right side here. Moving into acknowledgement, I'd like to thank several organizations and several people who have been very supportive to our project. First of all, USDOT, UTC, TIDC program for financial support, Connecticut Department of Transportation for a lot of support they have provided us. Mr. Haresh Dolakia, Mr. Manish Dodia, they have been working as our technical champion from Condat. We thank them very much. We have Metro North, Mr. Warren Best, another technical champion for Metro North, and Miss Hong McConnell. They have been very supportive during our field testing. Polytech Inc. and they've been good to us and very supportive of our research, loaning us their vibrometers. Mr. Mario Pineda, Aaron Vanderleet, and David Damiani. Thank you them all. University of Rhode Island, we received standalone accelerometers, Dr. Baxter and Dr. Wen Lee. We thank them too. University of Connecticut, Dr. Leslie Frame help us in the material testing. Dr. Shine Jiang, she's been nice providing us our prototype testing for our accelerators. A lot of students got involved in this project. They have got experience in working on this railroad project. They actively, 4 of them participated. Other 4 are supporting roles, and we have another 6 undergraduates who got experience working on this research. And thank to all of them. Some references we used for our study here. And finally, I would like to thank you for listening to this presentation. Now I'll be happy to answer any questions you may have. Thank you very much.